What is dark energy? We don't know what 70% of the universe is made of. Let that sink in. 70%. This invisible component is something we call dark energy. We don't feel it in our daily lives, but it's out there, pulling the strings of the cosmos, making the universe expand faster and faster. And the faster it expands, the more of this strange stuff seems to appear. But what is it? Why do we think something so bizarre even exists? Let's explore the evidence, the theories, and the wildest possibilities. This is the mystery of dark energy. The discovery. How did we discover dark energy? Let's rewind to the late 20th century. We already knew the universe was expanding, galaxies moving away from each other. Common sense said this expansion should be slowing down over time, thanks to gravity pulling everything back together. So, scientists tried to measure this deceleration by looking at exploding stars. Specifically, Type Ia supernovae. These explosions are incredibly bright and consistent, like cosmic lighthouses. They allow us to measure distance and look deep into the past. Because when we look at something far away in space, we're also looking back in time. In 1999, two independent teams studied the light from distant supernovae. And what they found was shocking. These stars were dimmer than expected. Which meant they were farther than they should be, suggesting the universe wasn't slowing down, it was speeding up. The acceleration. This changed everything. Instead of gravity dominating the cosmos, something else was pushing outward. A repulsive force. Some kind of cosmic anti-gravity. That's what we call dark energy. It's dark because we don't know what it is. It doesn't emit light. It doesn't interact with matter in any obvious way. But it does shape the fate of the universe. A quick pause. If you're enjoying this video and want to see more content like this, drop a like and subscribe to the channel. We explore deep science topics every week, so don't miss out. The cosmological constant. One of the leading suspects? Einstein's cosmological constant. A term he added to his equations to make the universe static, and later regretted when it turned out the universe was expanding. But ironically, the same term he dismissed might explain why the universe is accelerating. If space itself has an energy built into it, an energy that doesn't dilute as it expands, then it naturally causes expansion to accelerate. This fits perfectly with observations. And mathematically, it's the simplest explanation. So, is the cosmological constant the answer? Quantum vacuum energy. Here's where quantum physics joins the party. Even in a perfect vacuum, fields still exist and fluctuate. This gives the empty space a baseline energy, vacuum energy. And, guess what? When plugged into Einstein's equations, vacuum energy acts just like a cosmological constant. Problem solved, right? Well, not quite. Because if we calculate this vacuum energy using quantum field theory, the predicted amount is absurdly large, about 10 to the power of 60 times too big. That's a number with 60 zeros. It's the worst theoretical prediction in the history of science. The coincidence problem. There's another issue. Dark energy and matter have similar densities right now. But that's a weird coincidence. Dark energy stays constant. Matter dilutes as the universe expands. So why do they happen to match at this moment in cosmic history? It's like walking into a room and finding two clocks in perfect sync, by accident. That's called the coincidence problem, and it makes scientists uneasy. The dynamic possibility. What if dark energy isn't constant? Some theories propose a dynamic energy field, one that changes over time. A popular candidate is quintessence, a slowly evolving field that mimics dark energy but changes as the universe grows. This could solve the coincidence problem. And it also appears naturally in some particle physics theories. Still, these models come with complications: fine-tuning, weak forces we haven't detected, or exotic particles that may not exist. Modified gravity. Another approach. Maybe we've misunderstood gravity. Einstein's theory works extremely well on solar system scales. But on cosmic scales? Maybe gravity behaves differently. Some models suggest adding new terms to Einstein's equations. Others imagine extra dimensions where gravity leaks. Some even propose that the strength of gravity itself changes over time. These ideas are radical, but they try to explain cosmic acceleration without invoking mysterious energy. And yet, no modified theory has beaten the simplicity and accuracy of the cosmological constant, so far. Does dark energy even exist? One last possibility. What if we're just wrong about everything? Some researchers argue we may be misinterpreting the data. That maybe the universe isn't accelerating. That we live in a bubble-like region with lower matter density. Or that our models oversimplify the complexity of cosmic structure. While these alternatives are creative, they're harder to test, and most evidence still points to a universe that's accelerating. What's at stake? Why should we care? Because the fate of the universe depends on dark energy. If it's a cosmological constant, the universe will keep expanding forever, cooling down in a big freeze. If it grows stronger over time, we could face a big rip, where even atoms are torn apart. If it weakens, gravity might win back control, leading to a big crunch, a reversal of the Big Bang. We simply don't know. But whatever dark energy is, it holds the key to the ultimate destiny of everything. Thanks for watching. We publish new videos every week, exploring big science questions just like this one. If you enjoyed this, check out the rest of the channel. There's always more to uncover.